Hi, hello everyone. This is Devin, Runnels, and Bria-Goggins, and today we'll be demonstrating for our project 2, the stepper motor. As you see, we have some code here. We're going to show you today, but before we get to that, you might be asking yourself, what is a stepper motor? Well, the breakdown of the stepper motor is a brushless DC electric motor that divides a full rotation into several equal steps. The motor's position can then be commanded to move and hold at one of these steps without any feedback sensor and open loop controller. If the motor is carefully sized to the application in respect to the torque and speed, let me show how this all works on a software level. As you see here, we have code that is of the C# programming language, and that we input into the IDE, integrated development environment, that is, of Code Composer to output what we want with certain include statements. As you see, going down, we want to have certain include statements letting the computer know what we want to actually do. And then, like, include statements in C is meant for accessing XML comments in another file. Point blank, what we care about with the regards of a stepper motor is three things. Number one, whether the motor is on and off. So it's either on or it's off. The motor's direction, whether it's going to go forward or backward. And then the motor's speed, how slow it goes, how fast. What we're doing throughout the code is configuring the microcontroller to work with all registers. You set values to the different registers, and that configures the system clock, timer modes, GPIO functions, which peripherals have their clock enabled, GPIO states, direct register programming, which is straight up writing a value to a register, creates much faster execution time for the microcontroller to run than using any kind of API or library. Problem is, it takes much more time for the programmer to create code only in direct register access, especially with more complex tasks like controlling a LCD or USB applications. Direct register access has also no fail safes. You can do whatever you want. If you get a register wrong or a value wrong, there will not be any error from the compiler at all. So, direct register access is only advised in two situations. There isn't a function that does what you want, so you just have the option to do direct access. You have a vital piece of code that is time critical, so you need to use direct access to save execution time. See here, we have some defined statements. You define certain pins to go with certain things beforehand as to where you're going to call and what it actually is going to like pop up for the output. And then by defining a speed min, the speed will never go below that, and the max will never go higher than that. For certain problems, you might not actually want your motor to go over 800, as you see. It might cause a problem. As you see here, we have some comments with our code. As you see, if you want to go forward, you just clearly just press 0. Input 0, or if you want to go back, you can just clearly just change it to 1. And then you got stop and start. same ordeal. Full step, half step. We have long code here. Not too hard to understand. Full step routine. I just see void full step. Full step is the method that we're going to call. And this is how it goes about doing each thing to do a full step. Checking each case. It's a switch case we have set up. And then, as you see, we have a half step routine as well, to where we were going to show a demonstration of this here stepper motor doing a half step. This is also the switch case for that. Long. You have a handler for the timer, whether it wants to do a full step or a half step. This is our motor start method, to where we can actually sit here and start it up, start the stepper motor up, or stop it. Okay, now we have some update buttons that we have set up. Go through the code. Now this is the part where this is the void motor direction, to where I can change the direction. So it'll come through here. I can stop it on the dime and go back the other way. This is where we can alter the speed. And we can actually put a time, as you see right here, speed time, for the motor to go a certain speed for an allocated time, or actually even slow down at a certain rate, which is pretty cool. And then of course we have a reset. There are 3 commonly used excitation modes for step motors. These are full step, half step, and micro stepping. In full step operation, the motor moves through its basic step angle, i.e. a 1.8 degree step motor takes 200 steps per motor revolution. This mode requires the least amount of power from the driver of any of the excitation modes. The motor is operated with both phases energized at the same time. This mode provides improved torque and speed performance. Dual phase excitation provides about 30% to 40% more torque than single phase excitation, but does require twice as much power from the driver. Now, half step excitation is alternating single and dual phase operation, resulting in steps that are half the basic step angle. Due to the smaller step angle, this mode provides twice the resolution and smoother operation. Half stepping produces roughly 15% less torque than dual phase full stepping. Modified half stepping eliminates this torque decrease by increasing the current applied to the motor when a single phase is energized. Micro stepping, though, is a technique that increases motor resolution by controlling both the direction and the amplitude of current flow in each winding. Microstepping improves low speed smoothness and minimizes low speed resonance effects. Microstepping produces roughly 30% less torque. Dual phase full stepping.